The dominant strategy in artificial intelligence development is currently colliding with a strict, unforgiving mathematical limit that threatens to halt progress. For years, developers assumed that feeding a model more data and expanding its parameter count results in a proportional increase in intelligence. Compute required to process these massive datasets is growing exponentially, pushing training costs toward $10 billion. Simultaneously, the supply of high-quality human data is flatlining. The industry is hitting a structural ceiling. Capital expenditure alone can no longer serve as a defensible moat in this race. Moonshot AI is bypassing this compute barrier by replacing raw power with structural, algorithmic efficiency. Focusing on algorithmic efficiency, the model avoids soaring traditional costs. This creates an asymmetric economic environment. By drastically dropping compute hours, an open-source entity trains a 2.8 trillion parameter model at a fraction of the traditional cost. To understand exactly how this cost advantage is achieved, we need to examine the Thor-specific layers that make up the K3 architecture. This architectural stack points toward July 27, 2026, as the moment where efficiency overtakes brute force scaling. At the base layer, model training faces a memory bottleneck. Traditional optimization algorithms, like Atom, require massive amounts of GPU memory to update weights, a load that becomes unsustainable during a 2.8 trillion parameter run. The K3 stack solves this by replacing Atom with the Muon optimizer. By stripping out memory overhead, Muon allows the same hardware to process data faster and reach optimal performance in fewer cycles. Once memory is optimized, deep models face exploding gradients, where weight updates in the attention mechanism wildly compound and destabilize the network. K3 implements a KK clip. This mathematical threshold caps erratic spikes, locking the network into a stable state throughout the training process. Securing this base layer produces higher token efficiency, allowing the model to extract more cognitive value from each token without needing more raw data. Standard attention mechanisms scale quadratically. Doubling the length of text the model reads means computational cost quadruples until the hardware is overwhelmed. The Kim linear architecture restructures this process to scale linearly. Adding text now requires only a 1-to-1 increase in compute. With linear math, the memory ceiling is removed. The context window stretches from 128,000 to 1 million, even 10 million tokens. A 1 million token window allows a model to ingest a company's entire codebase or a complete corporate archive in a single prompt. Solving the quadratic scaling problem shifts the model from a conversational tool to a massive macro system capable of processing the daily workload of entire analyst teams in one single inference step. Simply expanding the context window isn't enough. In deep networks, vital information processed in the earliest layers often degrades before it reaches the final output. Developers typically use standard residual connections to combat this, bridging adjacent nodes to skip a single layer and prevent minor data loss. K3 introduces attention residue. This mechanism drives deep, structural bridges from the initial input layer all the way to the final outputs, maintaining gradient strength across the entire network. This mimics the biological function of the human hippocampus, enabling exact long-term recall regardless of the volume of information passing through the system. Attention residue ensures structural retention, making a 1 million token context window functional and reliable for complex data retrieval. Despite being trained almost exclusively on text, the K3 model achieves state-of-the-art computer vision capabilities. Traditionally, competitors build vision capabilities by training models on parallel arrays of raw images and text simultaneously, a resource-heavy approach. K3 relies on Zero Vision SFT, which processes language as a high-level mathematical abstraction of physical reality. By utilizing these text abstractions, the model reverse engineers visual geometry, generating precise object mapping without relying on visual training data. This pathway completely collapses the massive computational capital and physical hardware requirements that are typically associated with building multimodal systems. The completed K3 architecture is designed to function as a central orchestrator node within a larger digital network. This infrastructure facilitates the move from single tasks to multi-agent systemic problem-solving, known as agent swarms. Within these swarms, labor is compartmentalized. Discrete agents handle reading, coding, testing, and auditing, all working in parallel. K3's linear context and deep memory allow it to coordinate these agents natively on the Solana blockchain infrastructure. The combination of Solana's throughput and K3's orchestration provides the framework for an autonomous agent economy, reducing the latency and overhead typically associated with human coordination. This convergence of architectural efficiencies is projected to reach maturity on July 27, 2026. This date marks a transition where algorithmic efficiency yields superior performance relative to raw data scaling. This market matrix shows how the shift triggers structural margin compression for entities relying on the brute force closed-source paradigm. Independent vision AI startups face a specific risk, as their resource-heavy training models are challenged by text-driven reverse engineering. The Kimi K3 architecture demonstrates that structural algorithmic advantage, not billion-dollar compute budgets, is the definitive moat in AI development.